All right. So tonight we're going to be talking about a little optimization. Okay. And as you might recognize, optimization, get the best. And in math class, when we say the best, we mean either the maximum or the minimum. Okay. And so whenever you hear max or min, what do you think? Well, you think take the first derivative, set it equal to 0, solve for x. Okay, and that's true. And of course, as we said with the extreme value theorem, it could happen. It could be at a critical point. Remember this? We call this the critical point right here. X equals c. So on some interval from a to b, you will have a maximum at either one of the endpoints or at a critical point. So it could be this situation here. And on this interval, we would say that f of a is the minimum and f of c is the maximum at the critical point. F of b is neither one. Okay? It could be a situation like this. Here's a, here's b. Could be a situation like this, where it's an increasing function the whole time. If it's an increasing function, or it could have been a decreasing function the whole time, that means there's no place where it equals 0. There's no horizontal tangent line, so there's no critical value, at least in this interval. So you'd have a minimum and a maximum here and there. Could be a situation where on that interval you actually have 2 critical values. Or I guess 3 in this case. I got a little carried away. And this, of course, would be a maximum, and this is a local max. And, of course, this right here is a minimum, not, again, a local min, because apparently it goes down further. Okay? And so the overall minimum on this interval would be here at A. Looks like it's a little lower than that point. Okay? This looks like it would be the best or the highest in that region. And be careful when you say best. That sounds like max. That's true if you want to have the most bang for your buck. However, a lot of times we want to minimize our expenses. Now, almost everything we do, it'll be pretty obvious what you want to maximize. So one of the classics, and I'm just going to run you tonight through some of the classic problems of all times when it comes to minimizations and maximizations. Really what we're talking about is optimization. Okay. Now what I have here is a corral out there on the prairie. Old Farmer Brown's going to build himself a rectangular pasture. And assuming he's got enough ground, how big should he make the thing? What do you mean? Well, you can make it as big as you want to make it, right? Now, speaking from a former farmer situation, I wouldn't want to make it too blame big because, I'd rather have smaller patches. It's easier to catch the cows in, but that's neither here nor there. Really, what this all depends on is how much fence you have, or in other words, the perimeter. So we know that 2x plus 2y, okay, that's what it's going to be constrained by. So if I tell you the guy's got 1,000 feet of fencing, okay, that is how big he can make the pasture. Now, of course, he could take and put those 2 mostly 500-foot pieces side by side. Let's say 498, and then 2 feet, and then 2 feet, and 498 feet. And voila, you have 1,000 feet of fencing. I would argue that's not a very big pasture, though. Clearly, you can't get a whole lot of cows in there. They could stay in single file, I guess. They're not the greatest. And, of course, there's a variety of other things. So there's an idea where we have a happy medium. What's the best we can get? That's what we're interested in. Now, gosh darn it. Now, of course, what is area? Area, as we know, is x times y in this situation. So if I would like to maximize area, I would need to get area prime, obviously. But normally we have area prime of one number, of one variable, rather. So either area prime of x or area prime of only y. But here's the problem. I've got both of them in here. Often what you're going to have is you're going to have 2 equations. I can take this top equation up here, and I can solve for x. Oh, you stop it. Oh. Now I pissed it off. I could solve this top equation for... I don't really care what you're doing. I could solve it for y or x. Maybe I'll solve it for y. It's 500 minus x. And then what I can do what I can do is replace that and replace y with this variable right here. So now I can write that area is a function of x alone. And the area is equal to x times 500 minus x. Now if you're playing along at home, you're going, I recognize this thing, because that is, of course, 500x minus x squared. And you paid attention in pre-calculus class or something, so you know what this function looks like. Why, you know it's a parabola that opens down. And I happen to know where it crosses, but I'll just pretend like I don't for right now. Whoosh! Oh, look, it's got a vertex. That's where the maximum will occur. Nice! Okay? Now you're like, but Jay, I know how to factor this. Of course you do. Some people would say, well, the area, we said that may be equal to 0, so we did in Algebra 2, and we beat this into your heads until you were sick and tired of dealing with it, right? You factored it, and look, the area, the function, the y values, if you will, equals 0 when x is 0, or when x is equal to 500. Now come and look at that for a minute. If x was 0, you've taken two 500-foot pieces of fencing, laid them side by side, and you have exactly 0 area. That is no bueno. If x is 500, you've taken and you stacked them straight up in the air like this, and y is 0. And the idea being is that there's no area there. That's nice, but that's what we were doing in Algebra 2, but that's not what we're doing in calculus. What we want to do, okay, is we want to take the derivative here because, well, that's what we do. And so we're going to get 500 minus 2x, and then we're going to solve it equal to 0 because, of course, we want to know where are the critical value or values, where are they located. In this case, it occurs when x is 250. Well, now, friends, if x is 250, what does that make y? Well, up here, if you slap it in, you find it is also 250. Now, at this point, some people get angry. They're like, you said rectangle. Rectangle, a square is a rectangle, dog. It's okay. So when you have a rectangle that is 250 by 250, which, of course, is a square, this is the maximum area. Now, some people would say, well, what is that maximum area? Well, of course, you could multiply it out. Okay. But you know what's even cooler? Check it out. What would happen if you put 250 into here? You would get the same thing as taking 250 times 250. So that would be 625, and then I think 2 zeros. Anyway, square feet, and that's what you'd find out that it was. Okay. That would be the maximum amount of square footage he could build if he was using a rectangular pasture. Now, we could do this 100 ways. In the old days, we talk about, oh, look, here's a creek. And so you're going to build a rectangular pasture that borders this creek, but it's really deep, so swift water, your cow's not going to go across it, or it's really deep or steep or whatever. Okay? The idea being, you'd only fence 3 sides of it. And so your perimeter this time would be 2x plus a y, maybe equals 1,000, right? Because I'm only, again, depending on how many feet of fencing I have, I'm only fencing 3 sides of it. But look, your area is x times y again. But once again, I need to get rid of one of them. So over here, I do this. Right? So then the area is equal to x times 100 minus 2x, which of course is 100x minus 2x squared. So a prime is equal to 100 minus 4x. Put it equal to 0. X. Oops. That's 1,000, dummy. I knew that looked funny. 1,000 equals 4x, so x equals 250. Now you're like, it's the same. Well, not so fast there, partner. Because the x's are 250, but look, the y is 100 minus 500, or 1,000 minus 500, which is 500. Now, is this more square footage? Well, obviously, if you plug 250 into this guy, you will get that it's, twice as much square footage as we had before. Why is that? Because we could we could basically fence off a larger piece of ground with the same amount of wire. Okay? And so it's another classic example. I mean, here's another classic one. It's almost the same. Suppose you're going to cross-fence this piece of property into a bunch of little fences. Whee! Of course, y along the bottom. Check it out. Area is still equal to x times y. Okay? Whether you have a fence around your property or not, the area is the area. It's just the length times the width if it's a rectangle. But what is the perimeter this time? Well, it's going to be 4x. It's not really the perimeter anymore. It's 4x plus 2y is still equal to 1,000 because that's the only fence I have is 1,000. Well, it's the same thing except that it's going to look like this time. It's going to be 1,000 minus 4x divided by 2, which is 500 minus 2x, it looks like. Is that right? Feel like that's right. Cool. And so then you could stick this fella, again, in here for y, and you could do it again. And there's really no limit to these things. You can go nuts with them. Not very hard to do. You know, there's some other ones that are kind of fun to do. Suppose you have a rectangle with a rectangular prism, which just means a fancy way of saying a box, with a square bottom. Okay? So, x, 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 right? Now, I guess I drew it laying down. There's a reason I teach math and not art. Okay? So, your volume here is x squared times h, yes? And if I'm building a box, I probably do want to maximize the volume. I mean, that's a guess. Before I do anything else, I might want to maximize the volume. But something else is in play here, and that's surface area. So I think there's 2x squared, that's the top, and the bottom down here, dot, 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 right? And then there's 4 side pieces, right? And so, well, if I'm building this thing, let's pretend I'm building out of gold, I probably want to minimize the surface area if I'm just building the walls out of gold. I'd probably like to minimize the surface area, or maybe I want to minimize the cost. Cost and surface area typically want to be minimized. Volume might want to be maximized. So, I mean, you could do this problem a couple of ways. We could say for a given volume, minimize the surface area or minimize the cost. But over here it could be for a given surface area, maximize volume. So we do it both ways. We'll see what's up. I'm just going to go to a new page here. Let's say my box needs to hold 8 cubic meters. So in other words, I'm saying given this situation right here, then I would like to minimize my surface area. There's 2 of those and 4 of these guys. Okay? So I'm going to write it like this. Surface area you see right now is a function of both x and h. I need to get rid of one of them. Which would be easier? Well, h would be easier because there's just but the one of them. That's one reason. The other reason, hey look, it's easy to solve for h over here, isn't it? So now when I substitute, I get s as a function of just x. So I get 2x squared plus 4x times 8 over x squared. And if you clean your like terms up, you're going to get this plus this over that, which of course is the same as this dealio right here, right? And that's still the surface area. If you take the surface area prime, you're going to get 4x minus 32x to the minus 2, right? And what do you always do? You set it equal to 0 because we've got to find those critical values. So if I do this, if I'm doing this by hand, this is what I do, like this, right? X to the minus 2 is over x squared. I'm going to add that to the other side. And I'm going to times both sides by x squared. I'm going to divide both sides by 4. X cubed is equal to 8. So x is equal to 2. Well, check it out. If x is 2, friends, that means h is also 2. Which means that if we have a cube that is 2 by 2 by 2, it will meet the given volume specifications, and it will be the smallest surface area that I can come up with. Okay? So that's kind of fun. Again, you could do it the other way. You could say, look, I have 10 square meters or whatever of cardboard, and I would like to maximize volume. But notice that volume is x squared times h. That is, v is a function of x and h. It needs to be a function of only one variable at a time. Again, there's only but the one h. It's not squared. It would be pretty easy to solve for h here. And there it is. So now v is just a function of x by doing this. X squared times 10 minus x, or 2x squared rather, over 4x. And of course you can clean this up a little bit. This x will cancel. One of those will cancel. This is over 1. So you're going to get 10x minus 2x cubed all over 4. This is your v of x. Now, take the derivative of that. Okay, remember the 4 just stays put. It's a constant. So I'll just pull it out front. Leave it alone. Pretend it doesn't exist. So 10 minus 6x squared equals 0. Okay. You can time both sides by 4 if you like. And I'm going to add over to the other side. Divide by 6. The x squared is equal to 5/3, and I'm going to squirt that thing right there. That's my answer. Now this one I'm going to actually look at the graph of, see what's up on it. Now, we said that our answer was, it was parentheses, it was 10x plus, is it plus or minus? Minus 2x cubed. Divide by, oops, dang it, divide by 4. Nice. And check it out right there, that number. You're like, well, isn't it plus or minus? It does not make sense to have a negative side length. Okay, so in reality, that's another thing to think about. I talk about this quite a bit in my classes. I think about, well, wait a minute now. My y here is my volume. Are you with me? And I can't have a negative volume. That's just stupid. And I can't have a negative side length either. So what I've done here is I just pushed it down. What about the rest of the function? Yeah, what about it? It only makes sense between 0 and right here where it crosses the axes. By the way, right there and right there, if x was either of those two numbers, you'd have 0 volume, no volume. But here at this value, you have a maximum amount of volume. Now, interestingly enough, what is the square root of 5/3? 1.29. Oh, baby. Cha-ching. All right, there it is. So that's kind of how these deals always work. Now, you know, you could do varieties, all kinds of them. Another classic one, which is kind of in two pieces. So I present the first one first. You've got a lifeguard sitting over here doing a sunbathing routine. You know, you can think of Baywatch back in the day or something. I don't know. Okay, I draw this picture, and it's supposed to be ludicrous, right, when I'm drawing here. Okay? But what I want you to see is this. Here is a river. The current, or maybe it's not a river. It's just a very long swimming pool. By the way, you could put the current in there too if you wanted to, but that makes the problem a little messier yet. It's just a swimming pool. There is a kid drowning right here. And you're like, why doesn't he just pull himself out? I don't know. He's drowning. Why doesn't the lifeguard over here help him? Again, I don't know. I just work here. Okay? Help! Now, he happens to be 40 meters down the pool. Now you're like, holy crap, that's a big pool. It is literally a big pool. And the pool happens to be 30 meters wide. What are you trying to minimize here? The lady goes, oh no, I have to go rescue him. Now, how do I get there? Well, you could say, now some people would say, Jay, you run around the pool. Okay, well, no. This pool goes on for a long ways, like long ways in both directions. So she's going to have to swim. What are you trying to minimize here? Some people would say distance. Well, straight line distance on that hypotenuse would be the shortest distance. However, I don't think distance is what matters. I think time is of the essence. And I think time is what needs to be minimized. Okay? It's not distance that matters, it's time. Now, I don't know about you, but I couldn't, like, this is 50 meters, right? A squared, B squared, C squared, right? There is no way on this planet, if the devil himself was chasing me, that I could swim 50 meters. I don't think I could do it. I'm pretty positive I couldn't do it. Now you're like, this gal is a lifeguard. She's pretty fast. Okay, I'll give you that. She is probably a pretty fast swimmer. But unless you're Michael Phelps, you run way faster than you swim. And as a result, what we'd probably want to do is we'd probably not want to swim as far. We'd probably want to swim over into this region somewhere. Probably. And then run part of the ways. But what's it all dependent on? Well, as you know, back when you were a little kid, you learned this formula. Distance is rate times time. If you've been in physics, you realize we normally write it thusly. But time is equal to distance, or I'll actually go with D, because I'm probably going to use X in my formula here in a minute, is the distance divided by the rate. Well, the rate on land is different than the rate in the water. And, of course, these guys are both going to change. So we're going to have time for water, and we're going to have time for land. And when we add them together, we should get a total time. Oops. Stop it. This is total time. Oops. And I'd like this thing to be as small as it can possibly be. So here's the deal. Let's pick some numbers. Let's say in the water, she can swim at 2 meters a second. I don't know if that's fast or slow, and I don't really care. On land, let's say 3.5 meters per second. And again, I don't really know if that's fast or slow, and I don't really care. Okay? So let's think about this. If she swam the entire distance, again, being 50 meters, it would have taken her 100 seconds to get there. Am I right? No, I mean 100 seconds, you diddy. 25 seconds to get there, yes? Yay! Because 50 divided by 2 is 25. 25 seconds is a long time when you're drowning. I don't know if that's a good idea. Now, what if she swims straight across? Well, that would be 15 seconds to swim across. And then 40 divided by 3.5. If someone was here and could help me, that would be swell, but apparently I have to do everything myself. So 40 divided by 3.5 is 11.4 seconds to run down the beach. 11.4 seconds to run down the beach for a grand total of 26.4 seconds. Again, not very good. And by the way, longer than swimming the hypotenuse. But you're like, well, could we do better? Well, maybe. Maybe if we aimed somewhere in here. And if we aim somewhere in there and then we ran from here to here, let's see what we get. So let's call this distance x. That's why I didn't want to have it in the other formula. Then the hypotenuse would be 30 squared plus x squared, which of course is 900 plus x squared. And then she's going to run 40 minus x meters down the beach. And so my total time would be this distance divided by her rate plus this distance divided by her rate. This is time, and oh, by the way, it's a function of x. It depends on where she runs to, okay, where she swims towards, I should say. Now, how do you do the derivative here? Well, let's find out. Again, that half just stays out front. It's a constant. It doesn't hurt anything. Remember, the square root is really this. So if you bring it down, it's going to be times another half. 900 plus x squared to the minus a half. Ooh, it's a chain rule. The derivative of that is 2x. Plus, I'm just going to write this 1 over 3.5 out front. And then what's the derivative of 40 minus x? Why, it's negative 1. And once again, as always, set it to 0. So I'm going to get 2x over 4 square root of 900 plus x squared minus 1 over 3.5 equals 0. Now I will do this old school. I'm going to add this guy to the other side. I will show you how I would do it old school. I would also show you that I don't really care if you use a calculator to solve this equation, because this part right here, this part, this algebra, is not what I'm teaching you. That's not what this whole class is about. And so as a result, I don't really care if you do it that way, or you do it by hand. So this leaves me a 2 on the bottom, correct? So I'm going to multiply by 2 over to here, and I'm going to end up with 2 over 3.5, which is a number. I'm also going to multiply both sides by that, so it shows up over here. And what's it going to equal on this side? Just x. Some of you would have maybe multiplied by 3.5 to this side. If you did, you would have gotten this. Oops, 3.5 over 2x equals this guy. And it's not important at all which way you did it, because you get the same answer. So we're going to square the whole thing. So I'm going to get x squared is 4 over, I think this is 12.25. And then this is just 900 plus x squared. Distribute. Now I'm going to get a decimal for that if you don't mind, because I find it a little annoying. So I'm going to get 2 divided by 3.5. I'm going to 0.326, correct? So I'm going to have 0.326, that's this thing right here, times 900. So times 900. Oops, shoot. So 290, I'm going to go call it 294, okay? So 294, when you times that, plus, god dang, I can't remember what the number was. .3265 x squared equals x squared minus this fella over here come on, give it to me. There we go. You get 0.673. And then I'm going to divide. And I get 437 basically. So x squared is 437, square root. And so 20.9. X is 20.9. Was it meters, I think? Yeah, so meters, right? That means she should aim for a spot that's right here, 20.9 meters. Okay. So if you think about that, you plug it into here, this will tell you the distance, yes? It'll tell you the distance, and then you could divide by 2. And then you plug it into here, 20.9 into here, tell you the distance, divide by 3.5. Or, wait, you could literally stick 20.9 into that function. Now, so square root 900 plus x squared divide by 2 plus 40 minus x divide by 3.5. And, okay, Mr. J, you can't see it. This is terrible. You're right, can't see it. X is obviously a positive number, So the fact that I can't see it just means I didn't go over and up far enough. So I'm fine with those, but I'm not fine with these guys. So x, I'm going to go over to, let's say, well, if I went over to 40, that would be as if she ran all the way down the beach. So I know that's far enough over. Time is the y-axis, okay? And so we know that the most time we ever had was like 26 seconds. We figured that out earlier. So if I use 30, I know I've got it covered, made in the shade. And right there, 20.9. Bam! When x is 20.9, it will take her 23.7 seconds to get there. When minutes count, no. Okay, so the idea is we've minimized the time on that deal. Interestingly enough, that same problem can be done when you have water here and you need to run underground cable, let's say, from your, well, it looks like a field goal post. I was going to say from a, I was going to do a satellite dish, but I guess I drew an antenna. But whatever. You're going to run underground cable. And then, so underground on this side maybe. Or maybe I'm going to run it up on a wire, up on a post. You know, here's a post and here's a post. This kind of wire, or wire that's in a conduit underground, is cheaper than stuff that you'd run underwater. So clearly you'd want to minimize the amount of wire that you're putting under the water. It's exactly the same problem as the last one, with the exception, and it's a very small exception, is that now I want price. And price, as you know, is it's the unit price times the quantity, right? And so if it's sold by the foot, then if this was 40 feet or whatever, and then you went some x feet over this direction, this would be 400, not 400. Try again. 40 times 40 is 1600. There you go. Plus x squared. This is how many feet of fencing wire you would use, and then maybe the underwater wire is $50 a foot or something, or whatever. But on the side down here, you maybe want to run again 40 minus x or whatever we did a minute ago. This would be the amount of foot we would use, and on land it might only be 20 feet, $20 a foot. I mean. And the idea being is, wow, that is like 2.5 times cheaper. Bro, you would pretty much want to go straight across to get the least amount of underground cable you could. If they were exactly the same price, you would do this. Because that would be the shortest distance. You just wire it all underwater if they were exactly the same price. Or, in a weird scenario, if the underwater cable was cheaper, of course you'd do that. Okay. Back over here, if this gal was more Michael Phelps-ish, and swam at something like, I don't know, instead of 2, more like 3 meters per second, then she would end up swimming further this direction because she's faster at it. And the slower she gets, like 1, then it would come more over this direction. Because again, we want to maximize or minimize. We want to, in this case, if she is better at swimming, we want to maximize the length that she swims in the water. Or we don't want to maximize it, we want to encourage that to minimize the amount of time. It's like working toward your strengths, if you will. Okay. I think there's one more classic that I want to show, and then I think we'll probably call it a day for this. Pretty much, you'll see ones in the book. Ask if you have questions or you need more examples, of course. Of course, you can always Google stuff too, obviously. But another classic is very similar to that box problem. Another one of the classics is, well, what if you have a cylinder, a tin can, if you will. And that tin can needs to hold 500, cubic centimeters or whatever. It needs to, because you got to put your asparagus in it or something. I don't know. And so it wouldn't be x squared; it'd be pi r squared h would be the volume of that can, yes? Now the surface area for a can like this is what? It's 2 pi r squared. That's the lids, the top and the bottom, plus a 2 pi r h. That's the side. If you don't remember that, take a piece of paper and roll a piece of paper. Oh, I can't draw. Sorry. Roll a piece of paper into a circle, like into a cylinder. Yeesh, that's terrible. If this piece of paper had originally been 8.5 by 11, and you took the 11 and that's the part you twisted in a circle, that right there is the circumference, is it not? And so whenever you do this, it's the circumference of the top, which of course is 2 pi r times the height. That's how you figure that out. Now, since I would like to minimize surface area. To minimize surface area, I need to get rid of one of the variables. And again, h is probably the easiest one to get rid of. Right? So surface area, function of r only, 2 pi r squared plus 2 pi r h. So that would be surface area of r. I'm going to clean this up a little bit, okay? 2 pi r squared plus 1,000. The pi's cancel. One of the r's cancel over r. So surface area as a prime would be 4 pi r. Remember, this is r to the minus 1, so it's going to be minus 1,000 r to the minus 2. Again, set it to 0. Add this to the other side. Multiply both sides by r squared. And divide both sides by 4 pi. And then, of course, cube root the thing. So on my calculator, now remember, a lot of calculators don't have a cube root function. That's okay. Parentheses, 1,000, divide by 4 pi to the, and then make sure I always just make sure I use a parentheses. Most calculators, if you don't, will assume you mean to the first power and then divide the whole thing by 3. And that's not what I want. So 4.3 would be my radius. Okay? So the radius, 4.3. Now you stick that in over here, it'll tell us what our height ought to be. So, oops, what just happened? I don't know. Something's weird. No. Get down there. Alright, now. Excuse me. So 500 divided by pi times 4.3 squared is roughly 8.6, which is what it should be. Like, how do you know that, Jay? Well, I've been doing this a while. I'm an old man. Look, if the radius is 4.3, what's the diameter? Oh my goodness, it's 8.6. And the height is 8.6. Friends, you just made what's considered sometimes called a square cylinder. Okay? Now, you can get crazy with this thing. What if I told you that the bottoms of this cylinder, same problem, exactly the same problem. What if I told you that the bottoms and tops need to be made out of something that's more expensive? That was something like 10 cents per centimeter squared for tops and bottoms, and the side was something like 3 cents per centimeter squared. Now you're not going to minimize surface area. Now you're going to minimize tops and bottoms. You with me on this? By doing that, you're going to end up minimizing the cost. And so it won't be surface area anymore. It's going to be cost. And cost is going to be, well, there's 2 pi r squareds. And they each cost 0.1 plus 0.03 times the side amounts, which is 2 pi r h. And again, we know that from the last problem it was 8 over pi r squared. Was it 8? No, it was 500, wasn't it? Sorry about that. 500 is equal to h. So the cost, you see, is a function of r alone. If I do this, that's 0.2 pi r squared, 0.06, that's this times this, pi r h. And if you clean this up a little bit more, cost is a function of r, 0.2 pi r squared plus 0.06 times 500 should be 3, I think. Oh, 30, I lied to you. Sorry. That's what calculators are for, to prevent stupidity over r. And now, when I play the same exact game as last time, it's going to be 0.4 pi r minus 30 over r squared. Again, equals 0. So 0.4 pi r equals 30 over r squared. It's r cubed is equal to, so it's 5, so it's 150 divided by 2, so it should be 75 over pi, I think. But I'll check. 30, oops. You hippie. Yeah, 75 over pi. Oops, let's do that while we're here. So 75 divided by pi. Okay, oops, 75 divided by pi. And then, of course, what I want to do, I want to cube root that. And so if you cube root it, you get 2.88 is the radius. So the radius is 2.88. Am I shocked by this? Well, no, it's smaller. Why am I not shocked by that? Because I've just made the bottom smaller and the top smaller because they are expensive. What have I ended up doing? I've ended up making a very tall, skinny can. Okay? If the sides were more expensive, you'd end up with a tuna can. Okay? But they'd all hold the same volume. Now, of course, plug this baby in up here, you can find the new height. So it'd be, oops, I keep doing that. So clear, clear, clear. So 500 divided by pi times 2.88 squared. I've just made my can 19 centimeters tall. So this is a little ridiculous. 19 centimeters tall. The radius is 2.88, so this is roughly 5.76-ish centimeters across the bottom, because that would be the diameter. This time it's not even close to being square. It's ridiculously tall and scrawny. Okay. So yeah, that's kind of the game. Clearly some canisters, most canisters are all made out of the same tin / steel / aluminum, whatever it is. So the real consideration is what you're putting in it, right? I need to put this much soup in it, or I need to put this in it. If you're going to put asparagus spears in, well, you need a tall, skinny can. Tuna can go in literally anything. I'm not really sure what the story is on why it's a flat can, except if you ever buy the pink tuna in the soup-sized cans, it is sometimes hard to get the little crumbly tuna bits out of the bottom, okay? Or in that case, I guess it's salmon. This here is a little easier maybe to get the scraper into or whatever, I guess. But by the same token, why do you put tomato soup in one of these kind of cans, and then now you got to try to get the soup out of it? It's annoying, okay? But obviously some containers are built for certain things, others are built other ways. Others have been built that way. Maybe there was a reason in the past, more so, why than there is now. So it's one of those things, the classic story of all times is why were the solid rocket boosters, why were they on the space shuttle? Why were they only a certain diameter across? You know, wouldn't it have been better to build them a different diameter across? Well, it turns out that the reason they were shaped that size, okay, is because they had to go on a train from Utah, and to go through from Utah to Florida, they had to go through a tunnel. And of course, that tunnel is only so wide, and it's only so wide because there's, you know, tracks inside of it. And it's only so wide because the tracks have a certain narrow gauge. And the reason that gauge is what it is, which is 4 feet 8.5 inches in America. I think it's 4 feet 8.5. Don't quote me on that. It's some goofy number like 8.5. All right, and you're like, why is that? Well, and then they go on, and it's the same size the railroads were in England. Why were they? Because they built the railroads on the old Roman roads. Why were the old Roman tracks that far apart? Because it was the width of 2 horses' fannies, roughly. And so, you know, there might have been a reason why a tomato soup can was built the way it was back in the day, why it had that specific shape, because you could have made it any shape, okay? There's probably a reason why back then. Now we look at it and go, well, that's just what the shape it is, okay? But again, depending on what you want to build these things out of, you know, you want to minimize cost, you want to minimize surface area, do you want to maximize volume for a given amount of material? These are the things that come into question, okay? And so I hope that helps you. Again, give me an email if you need some help with it.